Okay, guys, so let's begin the class. Today we're going to start the last topic of mass balance that is called transient mass balance. Transient means that it depends on time. Okay, so all the processes that we have seen until today are processes that they don't depend on mass, so they're a continuous process. So what that means is that any property that you want to fix on is not going to change over time, right? The concentrations are not going to change, temperature, pressures, anything. Okay, so the, the process is going to be fixed at a one condition. Okay, that's the usual case for 24-hour processes, like for example, an oil refinery or well, any process where you refine a 24/7 schedule, you're going to find something similar to it. For example, in pharmacy, they do a batch process instead of doing a continuous. They do a batch. A batch means that well, you do the process one time, you produce, let's say, 1,000 pills, you start over and you produce 1,000 pills and so on, right? But for example, for I don't know the process to make soda or hops, right? What you do is a continuous process. Okay, so today we're going to fix on the transition process that depend on time. Okay, so for example, let me change to another program so we can share that part. Okay. Okay, so we're going to use this software again. And okay, so transient mass balance. If you remember, when we have a continuous process without chemical reaction, this is without, we have that the input is equal to the output, correct? But now, sorry, without reaction. But if we have a reaction, well, we have some of the components can be formed or consumed depending on if those are reagents or products, right? So right now I'm going to introduce a new term for the transient mass balance that is called the accumulation. Okay. So accumulation, we're going to, well, accumulation is more or less like it sounds, the amount of mass that remains in the system or that you're getting rid of in the system. That depends on time. So that will be equal to the input minus the output plus the generation minus the consumption. Okay, so generation and consumption are, well, if you have chemical reaction, right? Input and output, well, if you have an inlet and an outlet in your process, you're going to find those two, right? And accumulation is a term of how much stays in that system or that lacks in that system, right? Okay, so let me write a couple of things. For example, the input, you can interpret the input as the mass that gets in. That will be, for example, in kilograms per second, times the time that you're looking at it, right? So you have this variable time, and when you have time in seconds, you cancel those units, and this one remains in units of kilograms, right? Of mass in the mass input. And something similar happens to the output, right? You have a flow of mass and a change in time, and this again gives you the amount of kilograms in that particular system. Okay? So these terms about the mass flow, we have seen them before, and we're going to introduce a couple about generation. So generation, we're going to say there is a rate, so we're going to use an R, the rate of generation of mass times time. Again, you obtain kilograms, right? for the consumption, you're going to find again a rate of consumption. If you have any questions at any point, please unmute your microphone and let me know, okay? Because not I can't. I can know if you have doubts. Okay, so we have those terms, right? And we're going to introduce the term of the change or the delta in accumulation that we're going to call M right now. Again, so M. This M is the accumulation. Accumulation, we're going to define it as the same thing as we did up there. So accumulation is going to be the input, so it's the mass, the input minus the mass, the flow mass in the outlet, plus the rate of generation minus the rate of consumption, right? And this, of course, for the change of time, right? That this equation is this is the equation very important, right? Because with this you can know how much is accumulation. If you have mass left on the system that is getting accumulated, or if you have less mass each time. So let me put a picture here. Okay. So of course we are interested in not a specific time or in a lapse of time with the change in time, the delta time, the delta t, but we're more interested in the change of mass over time, right? So when I say the change of mass in time, well, something should tell you that it should be the change of mass is the differential of m over time, right? So how much it changes over time. So this again will be the inlet minus the outlet plus the generation minus the consumption, right? Okay, so you have a differential equation for that. Pay attention to this previous page that if we have a continuous process, the delta t over here, well, mass is not going to change over time, so this term will cancel the change of mass on time, and that will be equal to the same equation that we have for continuous process in mass balance. Okay. Okay. So to solve a differential equation, we need, besides the differential equation, that is the one I just wrote, we need a boundary condition, right? Boundary condition. So a boundary condition tells us what is the state of that process at some time, right? Would be most often is at time zero, right? Well, this is an example, right? So an example at t0, m will be equal to whatever, right? To any mass or a volume or something, right? Or you can say it like this, that m, the mass at time zero, is equal to something, right? This is going to be more clear in an example in a couple of minutes. Okay, so to solve, we're going to see two parts of a transient mass balance: the differential mass balance and the integral mass balance. Okay. So the first step for the differential mass balance is to obtain a differential equation and a boundary condition. Okay, so we can do that in an example, right? Okay, so let me change this page. So we have this process, right? Differential balance on a chemical reactor. Okay, it says a continuous steroid tank reactor is used to produce a compound R in the liquid phase reaction A that changes or reacts to R. Feed enters the reactor at the rate of V0 in liters per second. The concentration of the reactant in the feed is Ca0, so the concentration of A in moles of A per liter. The volume of the tank content is volume in liters. The vessel may be considered perfectly mixed, so that the concentration of A in the product stream equals that in the tank. For this process, the rate of consumption A equals constant K times the concentration of A in the reactor. That is given in units of mole divided per second per liter of the volume of the reaction of the reactor. All fluids, the feed, the tank content, and the product may be taken to have the same density, so a constant density. Write differential balance on the total mass. That's one part, the total mass, and on the moles of A, right? Expressing the balance in terms of the variables in the following diagram. So in that diagram, what we can see is the conditions, right? The inlet is the inlet is a flow, volume flow, right? A density and a concentration, initial concentration, right? And then we have the reactor with a stirrer here, right? And the concentration is you're going to have a concentration of A, and of course you're going to have a concentration of R that it's being produced, right? But we're not going to pay attention to it because we only need the total mass and the moles of A. And the concentration at the exit is flow, right? Flow volume density that we can assume that is the same density as in the inlet as in the reactor, and the concentration of A, right? So we have that particular system, and now we have to, well, the first thing to do is to write down the equation that I just showed you, right? So accumulation, it's equal to the inlet, to the input, minus the output, plus the generation, minus the consumption. Right? So we're going to pay attention first to the total mass. Okay? To the total mass. So in the total mass, you're going to find that, of course, there is an input because we have a volumetric flow in the inlet, and we have an outlet that we have a volumetric flow the outlet. So these two, we know that we have them, right? But the total mass, well, the total mass can be generated, right? The total mass is conserved. So the term of generation is not going to appear in the total mass balance. So we cross that one. And consumption, again, mass should be constant. So again, we're not going to have consumption. So we're going to cross that one too, okay? So if we do that, our equation is just that accumulation is equal to the input minus the output. And that's it, right? Okay.
Professor,
yes.
why wasn't there consumption in the system?
Uh, right now, because we're paying attention to the total mass of it, right? And total mass, okay, A is going to react to form R, but the total mass is not going to change, right? The number of atoms in that system is not going to change at all, right?
Right.
So that one.
Thank you.
You're welcome. Okay, so the first thing to do is to write the mass. How can we interpret the mass in the system, the total mass inside of the reaction, inside of the reactor, as a mass, right? So M. M is the mass, right? M is the mass and should be in, let's say, grams, right? On any other unit that you want of mass. And that one, with the variables that we have on the diagram, if you pay attention, we have the volume of the tank, we have the concentration of A and the density, right? The density of all the solution that is on the tank. So the concentration of A, of course, doesn't matter for the total mass, but the volume of the tank and the density can give us the mass, right? If we have the volume that is in liters, we multiply it by the density that is in grams per liter. Well, with that one, we obtain the mass, right? And that's an important term. At all times in transient mass balance, what we have to do is to start either with the mass or with the moles of something, right? The equation can convert into into different differentials, as we're going to see in this problem. But you have to start either with mass or with moles. Okay, always. Okay, so that one. Then we have to write down the. Now we have to write down the accumulation, right? The accumulation, we know that is the change of mass over time. Okay, so we do that exactly, right? The change in mass will be the differential of the volume times the density divided by the time, right? We know because the problem says so, and we are going to assume it's correct. The density is a constant, so we can take it out of the differential, and we end up with the change in mass over time is the density times the change of volume over time. Okay. And then we have to write down, so this was the accumulation, right? Then we have to write down an equation for each term. So in this case, we're going to start with the input. So the input we have the volume that enters the system, or the flow, well, the volumetric flow that enters the system, and we have the density too, right? So if we have the volume that enters the system, this is in liters per second, we multiply it by the density, that is in grams per liter, we obtain units of grams per second, right? That is the same. That is the same units as here, right? Grams per second. Okay, sorry, grams per second, grams per liter. So grams per liter, right? Okay. And then we are going to write the output. The output again, we have a volumetric flow and we have density, and with that one we can obtain the change, well, the mass, right? So it will be the volumetric flow in the outlet, again, liter per second times the density in grams per liter. Okay. And now, well, we have all the terms that we have for this particular mass balance, that is the total mass. So we can put all the terms together, right? So we're going to have that the density times the change of volume over time is going to be equal to the density times the volumetric flow in the inlet minus the volumetric flow in the outlet. That's it, right? We have only that. And we know that the density is a constant, so we can cancel all those terms. Density equals to density, and we obtain that the change in volume over time is equal to the volumetric flow at the inlet minus the volumetric flow at the outlet. And this is our differential equation. Okay, well, we said that for a system to be complete, we need a boundary condition too, right? So that boundary condition in this particular process, uh, we have that at the beginning, before any of the reaction happens. We know that the concentration inside of the tank should be the initial concentration, right? Is Ca0, right? So at time zero, we know that the concentration of sorry, concentration, in this case, sorry, stepping forward. In this problem, we have that the volume, we can say that the volume inside of the reactor is going to have initial volume, right? We don't know that volume in number right now because it's just an analytical problem, but we can have that condition, right? That at T0, the volume is going to be a fixed volume that it's a constant, right? And with those two, we'll have the system, a complete system of differential equation with the boundary condition, and we can solve this problem. Okay, if we had the numbers, of course. We don't have those, so we're not going to solve it numerically right now. Okay, so that is the first part of the problem. The second part of the problem is to solve the moles of A, right? Do a mass balance of the moles of A. Before I continue, Do you have any questions about this part? How did I reach to these equations? Okay, so we're going to do the same exact thing as the to obtain the balance on the moles of A, right? So we begin with our equation, with our initial equation for this kind of system. So accumulation is equal to input minus output plus generation minus consumption. And we have to see which of these terms stay if we have the balance on the moles of A, right? So we have an input of moles of A. Well, yes, right? We have a concentration over here in the inlet, initial concentration of A. So yes, we have an input. An output, well, yes, sum of A is not going to react completely. So we're going to have a concentration that should be lower than the initial, of course, but we're going to have an output, yes. Then a generation. Well, we have a reaction where we have that the A reacts to form R, right? That it's over here. So a generation, no, we don't generate A, right? It's a reagent, so it's going to be consumed. So generation, we don't have it, and consumption, as I just said, you're going to consume some of A because you have a reaction. So we have a consumption of A, right? So we have those three terms. And again, we need to start with either the mass or the number of moles of A in the reactor. So I'm going to start with the number of moles because it's the thing that we want, right? It's what the problem is asking. So the number of moles of A inside of the reactor, well, we know the concentration because it's Ca, right? And we know the volume that is Bl. So if we multiply V, that is in liter, times the concentration of A, that is in mole per liter, we obtain the number of moles of A, right? So that is our initial part, and then we have to say that the accumulation should be equal to the change of Na, the change of Na over time, right? And that is, of course, the change of volume times concentration of A in the reactor over time. Okay? And then we do the same thing, the same steps as we did in the other problem, and we start with the input. So the input will be the input of A would be the volumetric flow in the inlet times the concentration. Sorry, this is in liters per second. And we're going to multiply it by the concentration of A, the initial concentration, so Ca0, right? That is in moles of A per liter. And this, if we cancel the units of liter, is going to be in moles of A per second, right? That would be the appropriate units for the accumulation too, right? It's the number of moles divided is the number of moles over time, right? So number of moles per liter per second. Right. Okay, so that is the input, and we have the output too. That will be the volumetric flow again in liter per second times concentration in the outlet. That is the same one as in the reactor, moles per liter, right? So again, the same units. And the last one is the consumption, right? The consumption over here in the problem, it tells us that for this process, the rate of consumption of A is equal to a constant. And if we see the units here, it says moles divided per second per liter of reaction volume, right? So to obtain the number of moles per second of consumption, we need to add the volume in the tank, right? Because if not, the units are not the correct. So K, that is the constant times the concentration of A, right? That one is the consumption. This one is in moles per second per liter, right? And then we have to multiply by the volume in liters, right, of the reactor, inside of the reactor. So if we cross the units for all the systems, liters, 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 we obtain mole per second in all cases, right? And the only thing that we have to do now is to plug in everything into our initial equation that is over here. Accumulation is equal to input minus output minus consumption, right? So we do just that. We have the change of volume times the concentration over time by the accumulation is going to be equal to the volumetric flow in the inlet times the initial concentration of A, minus the output, that is the volumetric flow at the outlet times the concentration of A in the reactor, and minus the rate constant times concentration of A um, per volume, right? And that's it. This is our equation, right? And now we have a differential equation, and the only thing we're missing is, well, of course, the boundary condition. Okay, so the boundary condition for this system, if you pay attention to the system, we have that at the beginning, before we turn on the reactor, it will have some volume of this of A. We're going to have a concentration inside that is going to be the initial concentration, right? The CA0, because, well, that's at the beginning, right? Before any reaction happens. So at T0, we have that CA, it's equal to CA0, right? And that's it. We have we have our differential equation that we want to solve, and we have a boundary condition. And then, of course, we can complete this system if we have all the properties or all the numbers. Any questions for the moment, guys?
No.
Okay. Okay. So that is the differential part, right, of the balance. But as I told you, we have an integral part. Mm, an integral balance. Okay. So in the integral balance, what we have to do is, well, to solve that equation. Okay. And to solve a differential equation, well, what we do is most often what we do is to separate variables, and with those variables separated, we can integrate over those, right? So if we start with our general equation, mhm, right? If we start with this equation, uh, we can we can rewrite this equation as dm differential of m is going to be equal to all that here, that depends on time, right? And that, of course, we can solve that one, right? Integrating. So if we do the integral of this, we're going to have the integral of the differential of m that we're going to integrate from m to m from t0 to tf, all the initial. So this would be, of course, the mass at the final time minus the mass at the initial time, right? And this would be equal to all those terms integrated over time, right? So T0, Tf of the input and differential temp of the time plus T0 Ef for the generation, differential of time, minus the integral of TCO to TF of the outlet, the mass that get out, differential of time, and minus the integral of 0 to TF of the consumption. Okay, differential of time. Okay. So if we have all those terms, of course, we can reach to a numerical result, right? Or we can do it to analytically, right? And so if we solve this, if we solve any equations that we have by doing separation of variables and integrating, we can obtain well the change in mass or how the mass behaves over time, right? Now that's the interest of of this kind of balances. Okay, so again, I think it's easier if we do example. Okay, so the first thing, let me read the next problem. I will ask you to do something, and then I will finish the resolution of this problem. So it says a water balance on a city reservoir. It says the water level in a municipal reservoir has been decreasing steadily during a dry spell, and there is concern that the drought could continue for another 60 days. The local water company estimate that the consumption rate in the city is approximately 10 to the 7th liters per day. The State Conservation Service estimates that the rainfall and stream drainage into the reservoir, coupled with evaporation from the reservoir, should yield a net water input rate of 10 to the 6th exponent of minus T divided by 100 liters per day, where T is the time in days from the beginning of the drought, at which time the reservoir contain an estimate 10.9 liters of water, okay, at the beginning. Okay, so it says write a differential balance on the water in the reservoir, integrate the balance to calculate the reservoir volume at the end of the 60 days of continued drought. Okay, so that's the first point. This first part is what you have to do. Okay, so I'm going to give you around 10 minutes to do it. Okay, to write a differential balance on that one. Okay, remember that you have to write the differential balance and to put a boundary condition to solve it. Okay, so do the same thing as I did in the previous example. Write down the equation, the complete equation. Accumulation is equal to input minus output plus generation minus consumption, and see what terms do you have in that particular equation from the text that you have, and then separate each term, right? How can I calculate the mass in the reservoir? How can I calculate the mass that gets in, out, or whatever you have, and then find a differential equation. Okay. So please begin. Yeah, we can do it individually, and if you have any questions, please let me know. You have around, let's say, 10 minutes or something like that. Pay attention to the variables that you're given, right? If you pay attention, all of those are in liters per day, right? So that is a needed information for this problem, so you can solve this problem. Do you have any questions, guys?
O sea, yo creo que, o sea, podemos resolverlo entre todos porque como que los valores de que entran y de todo esto como que no sé si lo estoy sustituyendo bien y así.
No, por eso, o sea, el chiste es que ustedes lo intenten, ¿no?
Sí,
La primera parte, la parte del análisis diferencial, y ya luego pues, lo vamos a resolver todos, claro.
ok, va. Gracias.
Ujú. Are you almost done with the differential equation, guys?
Yes, yes,
Okay. Okay, so let me start the solution of this problem, okay? We are going to solve the first part, 2, so 1. So write the differential balance on the water reservoir, right? If you pay attention to the units of all this, all the information that you have, it's in liters per day, liter per day, right? So that means that we have to obtain an equation that uses the volume of it, okay? So as I told you before, we start with the general equation. Accumulation is equal to input minus output plus generation minus consumption. Okay. So here we have that it says that the consumption rate in the city is approximately 10 to the 7th liter per day, right? So we can use that value for two different things, either for a consumption or for an outlet. Okay, either way is going to be the same thing, right? So because mass is conserved, I'm going to put it as an output. Okay, so I'm going to say that we don't have consumption of water, right? We're going to have an outlet from that reservoir. Okay, and then the generation. Water is not going to be generated, right? Because again, you have a mass, you have a constant mass of the system. So it goes down generation, and we will only have the inlet, the input, and the output. Okay. So the accumulation, again, we have to start with the mass, right? So the mass of the reservoir is going to be the density of the water times the volume of that reservoir, right? And then we can obtain, of course, the change in mass over time going to be equal to the change of the density times the volume over time, right? And then we have to find the two terms. So the input we know that says that the reservoir should yield a net water input rate of 10 to the exponent of blah blah blah, right? So that is our input. Okay, so input is equal to 10 to the sixth e to minus t over 100, right? That is our input, and the output is just this value over here. And it says that the rate consumption is approximately 10 to the 7th liter per day, right? So we have that 10 to the 7. And of course, if we find these values that are in liters per day, we have to multiply both terms by the density. If not, we are not obtaining mass, we're obtaining just volume, right? And the generation and consumption, we said that we didn't have any, right? So those are the terms that we have for our equation. And then we can plug in everything together. So the change of the density times the volume over time is going to be equal to the density times 10 to the sixth e to the minus t over 100 minus 10 to the 7th. Okay, and that's it. This is our differential equation. And of course, if we assume that the density is constant, that it's a good assumption because it's water and it's going to be at the same temperature, so that the density shouldn't change. So we can cross density and density. Okay, so we end up with that differential equation, and then of course we have to express this with a boundary condition. So at time zero, at the beginning of the drought, we had we had an estimate. It says at which time, at the beginning of the drought, which time the reservoir contained an estimate of 10 to 9 liters of water, right? So that is our initial condition. So the volume of T0 will be 10 to the 9 liters. Okay. And then we have it, right? That is the first part The first part of this problem is to obtain the differential equation and a boundary condition. Okay, so now we have to just integrate the balance to calculate the reservoir volume at the end of those 60 days, right? It's giving us a time frame of continuous drought. Okay. So now what we have to do is well to solve this equation doing the separation of the variables, right? So let's do that, right? If we separate the variables of this problem, we obtain that dv it's equal to 10 to the sixth e minus t over 100 minus 10 to the seventh. And this the differential time, right? But we know the time frame that we want, right? So we want the time frame from the beginning of the drought to 60 days, right? And we know that all the conditions are per day, right? So we can use that time frame and we can integrate over that time frame. So the integral of the volume from B0 to B60, so B60 days, right, would be equal to the integral of from 0 t0 to 60, so 60 days, right, of the both parts of this equation. So over t from 0 to 60, 10 to the 7 et, right? So the first part of this equation, this one, is pretty easily converted. It's just the volume at 60 days minus the volume at the beginning of the drought, and would be equal to the differential equation, right? This other term, the term in blue, I'm going to write here. It's of course really easily integrated. This is just put it over here, so you can have the different parts of it. That's it, right? Just over t. Sorry, this is negative. And then we solve the last part that because we write it down in green. So we solve the last equation. And because 10 to the 60 is a constant, we can take it out of the integral. So it's 10 to the sixth integral from 0 to 60 of t minus 100. Okay. So here what we can do is to solve this equation. We can assume that we're going to change the values to EU and DU. So we're going to assume that U is equal to minus t over 100. So we can have the integral of e to the u, and the u is going to be equal to minus t over 1. Sorry, 1 over 100 the differential of t. Okay, so if we solve dt, we're going to find that is 100 u. Okay, so if we substitute all this, you're going to find the differential equation that we want to solve is minus 100 EU du, and the solution of this one is minus 100 EU. The integral of EU is EU, right? So we can substitute those up here. So we have 10 to the sixth times 10 to the 2, which is 100. And EU, that we said that EU was minus t over 100. Okay. So I'm going to need another page to write down everything.
Can you go back a little bit and wait,
Yes,
please?
of course.
Thank you.
You're welcome. Okay, so now let's change the part of this problem where we put everything together, right? So the volume at 60 days, that is the one that we are interested in. Let me do something over here. Okay, so B at the 60th day, it's going to be equal to the volume that we have at the beginning, so 10 to the 9, right? Minus 10 to the, yes, 10 to the 6 times 10 to the 2, that is this E to the minus T over 100. This evaluated from 0 to 60 days, and minus 10 to 7 T evaluated from 0 to 60. That's it, right? Then we have to substitute the values for each part. So we have this minus 10 to the 6, 10 to the 2, e to the 60 over 100 minus 10 to the 6, 10 to the 2, e to the 0 over 100. Sorry, this is a plus because we have two different signs. And then minus 10 to the 7 times 60. So minus minus, so plus 10 to the 7 times 0, right? That's it, right? If we solve this equation with, of course, a calculator, we obtain that the volume at the 60th day, we have, in theory, 4.45 times 10 to the 8 liters. Okay? So this should be the answer to that problem. And if we have a value over 0 liters, it means that we're going to have water still after the drought, right? So any questions for this problem? How did I solve it at any point?
I have a question, teacher.
Yes.
Why in the previous page, why do we multiply the input and the output with the density?
Because if not, you're not going to have a mass, right? You are having, what you need is a mass balance, right? So if you only have the numbers 10 to the 7, for example, 10 to the 7 is liters per day, right? So
Okay.
in that case, you don't have a mass if you multiply that, right? You need to obtain a mass because we're doing a mass balance. That's why we started with mass. You need to multiply for the density of the fluid to obtain the mass of that fluid, right? Of that volume,
Okay.
or whatever, right? That's why.
Okay.
You could start with volume, and you're going to know that. Well, you're not going to need these densities, right? But that would be incorrect because you're doing a mass balance, not a volume balance. Okay, so the equation that you can obtain at the end could be in volume or could be in many other variables, but at the beginning you have to start with the mass.
Okay, teacher. Thank you.
You're welcome. So the steps are, well, as I told you, for a continuous mass balance. For transient mass balance, well, you have to do a couple of steps every time to ensure that you're doing it correctly, right? The first one is to write down the equation that we have over here, right? The first one, accumulation, it's equal to the input minus the output plus the generation minus the consumption, and see what terms of that equation you're going to have at the end, well, for that particular problem, right? Then the second step, so this is step 1, right? The second step is to write down the mass. the mass, how to calculate the mass of the thing that you want to calculate, of course. It could be the moles of something, so you would use the number of moles instead of the mass, but it can be the mass of a particular thing instead of just the whole system. Here was the whole system, but it can be the mass of a small part of the system, right? And then with that, you obtain the differential equation for the accumulation, so 3, right? dm over dt, and you can express it through the variables that you have on the problem. And then the first step is to find the terms that you had in the equation. In this case, input and output, to find an equation for each one, right? Then the fifth step is to have everything in an equation, in a differential equation, and to have a boundary condition to be able to solve this problem. And when you have all that, the sixth step is, well, to integrate this, right? To do the integral part of the integral balance, and then to obtain the result. Okay, if you follow those steps, you're going to be able, well, most of the time, to obtain the result of your problem, right? So, okay, I don't know if you have any questions for this part. Okay, so the last part of this class of today is going to be to do it's a brief activity. You can do it individually. It's already on Blackboard. And it has to do with these transient mass balances. Okay, the part that I'm most interested on is in the last part. Let me see if I have it here. So if you go to Blackboard, please, and go to activities, you're going to find an activity that is called transient balances. Okay, so let me share it with you.
Profe, ¿podría poner la última hoja del ejercicio, por favor?
Okay, so please go to Blackboard and start opening the document, please. What was your question about this last part?
No, no tenía preguntas, solo no copié. Gracias.
Yeah, let me know when you're done.
Ya, profe. Pero entonces, ¿eso significa que sí van a tener agua suficiente o no?
Sí, ¿no? Porque tienes una cantidad de agua positiva, ¿no? Entonces lo que te está diciendo es que al final de los 60 días de sequía te van a quedar 4.45 por 10 a la 8 litros en el ahí se olvidó cómo se llama esa cosa en español. Bueno, en el lugar de la reserva de agua, ¿no? O sea, si vas a tener agua al final de la sequía y pues todos estarán. Bueno, entonces, so this is the activity that you have to do for today. You don't have to finish it right now in this instant. The first part is more or less the thing. Sorry, guys, I lost my connection for a second. Can you hear me okay again?
Sí,
Yes.
Yes.
Okay, so as I was telling you, this is the activity. Okay, it's in Blackboard already. So the first part is to define the terms balances and transient processes, differential equations, is the initial value and boundary condition for differential equations, of course. That is the first part, and then you have to look for a video or for a process, and you have to describe what happens and what you want to determine and which are the variables that depends on time. So, for example, whatever you want to, as long as it's a process that depends on time, and you have to determine which of the variable depends on time, so the mass, volume, concentration, density, temperature, and so on, right? So in in the activity that you upload to Blackboard, please add the link to the YouTube video or wherever you found the information, so I can see it and to see if you are correct about the variables that change with mass. Okay. Then the type of problems that we're going to look, in the types of problems that we're going to solve, we're going to find two different types of differential equations. One, there is the type of differential of a constant times variables that depends on x, or also the time in time. And the second type, that it's two variables, y1 and y2, that depends over differential equation, in this case x. Okay, so for these two types of differential equations, you have to find a methodology to solve them. Okay, and that's it. Well, you find that information, you load that file to Blackboard today. That's pretty much it, right? On Thursday, there is our last class. We're going to do a couple of different problems about transient balances, and if I have time, I will give you like a brief course of mass balance of all the course. Okay, I hope I have the time for that. Okay. If not, maybe I would record it on video and then I will upload it so you can see it. Right? It will be like a brief class on all the things that you should know about mass balance. Okay. Do you have any questions about activity or anything else?
Profe, yo tengo una duda. ¿Va a haber asesorías antes del final?
Sí, pero o sea, por el momento tendrán que ser así como, bueno, como las que hemos tenido, pues.
Ok.
Profe, es que yo quiero una asesoría porque tengo muchas dudas del proyecto final. No sé cuándo pueda.
Y no puedes en Zoom los días que tenemos asesoría, que son los miércoles y jueves.
Ah, sí. ¿A qué hora es?
Híjole, déjalo checo porque no me acuerdo bien. El miércoles es... No, el miércoles es de 10 a 11 y
Ok.
los jueves de 11 a 1.
Ok, gracias.
Entonces, de hecho, yo, digamos, todas las semanas he estado ahí conectándome, pero la verdad es que en general casi nadie se conecta. Pero yo ahí.
Ok. Gracias, profe.
¿En qué horario, profe? Perdón. De...
Los miércoles de 10 a 11 y los jueves
Ajá.
de 11 a 1.
Vale, gracias.
Profe, ¿y estas actividades para cuándo son?
Esta actividad es para hoy.
Ah,
Bueno,
ok.
que la suban antes de la siguiente clase, está bien.
Ah, o sea, es para... Ah, ok, gracias.
Sí, porque la verdad es que ya nos queda poquito tiempo, o sea, nos quedan 10 minutos, que no van a acabar la actividad en 10 minutos, obviamente.
Profe, ¿el proyecto final lo traemos impreso el día del examen?
No, lo suben a Blackboard.
Ok.
Ok.
Sí, para no andar gastando papel, no hay necesidad.
Profe, y otra cosa, en la parte que dice las variables que dependen del tiempo, o sea, podemos poner como ejemplos, no sé, así como, pues, o sea, si es la presión, temperatura, volumen, pero nada más así enumerarlas o hay que explicarlas o así.
Pues explicar un poco del por qué dices que depende del tiempo, ¿no? En ese proceso,
Ah, ok, va, gracias.
para que quede claro el por qué es diferente del tiempo, ¿no?
Va, gracias.
Vale. Entonces, bueno, pues yo aquí estaré en los siguientes 10 minutos por si tienen dudas de la actividad o alguna cosa. Y pues si no tienen dudas, pues nos vemos el jueves para resolver problemas de este tipo y a ver si nos da tiempo de dar la reseña rápida del uso de balance, ¿no?